Okay, my name is Dmitri. This is physiological cortisol control in Addison patients with pump-based hydrocortisone. My mentors were Salman and Ching, and this was for my spring 2026 advanced project. And what I will talk about is first the background behind cortisol, Addison's disease, and treatment strategies with hydrocortisone, and then how we formulate the problem from a control perspective, and also how we'll evaluate it. And then I'll walk through the two-compartment physiological and medication model that we came up with and how we characterize patients that way, as well as the healthy data set. And then the LQG optimal control design and how this was then simulated and constructed, and then the actual results and analysis beyond that. Okay, first, cortisol. This is the body's natural corticoid. It's basically a steroid that's released by the adrenal glands, and it does a number of things in terms of regulating blood glucose, the immune activity, and also the stress response, as well as your energy levels throughout the day. Um, Apart from this, it's very important to understand that the daily timing and the amplitude, or basically the circadian rhythm throughout the day, is very, very important to regulating quality of life. Um, you can kind of characterize it on the side. This is an example of basically what a healthy reference would look like throughout the day. So you generally can characterize it into a number of phases. So you have a morning peak where you have a high level of cortisol in the blood. And what this means is you can wake up and have high energy. In the afternoon, this starts to plateau, and then in the evening, it becomes very low, so that you have lower energy and you can basically be prepared to sleep. And then while you're sleeping, your body actually creates a reasonable amount of cortisol, so that when you wake up, you can repeat the cycle. So this circadian rhythm is very important for healthy cortisol or healthy endogenous cortisol production. And so the disease that we're interested in is Addison's disease. It's also known as primary adrenal insufficiency. Primary meaning the adrenal gland is actually that's within this HPA axis has become unresponsive to ACTH stimulus and no longer releases cortisol, at least to the desired level to mimic the circadian rhythm of a healthy subject. And what that means is you have basically very, very low cortisol in the blood throughout the day. This is a lifelong disease that progressively onsets from the autoimmune destruction of the adrenal gland. And essentially, when you have Addison's disease, your body can no longer release cortisol. And because cortisol is very important to many different aspects, so immune function, energy levels, metabolic regulation, what you have is generally many symptoms that are very uncomfortable for the patient. So this is GI issues, hyperpigmentation in the skin, weight loss, weakness. This is primarily associated with low energy. And this is mainly because the adrenal gland is no longer responsive and the HPA axis feedback loop is essentially broken. So talking about how the staging of Addison's disease onset is very important, especially for our work. So primarily when we talk about number of stages, we can say the normal adrenal function. This is when you have normal plasma ACTH in the blood. You have normal adrenal function, and you have normal cortisol response. This is basically saying the adrenal gland is satisfactorily able to respond to ACTH stimulus and then release cortisol, so there's nothing wrong here. As the adrenal gland basically becomes further deteriorated, you have less response to the ACTH. So this kind of becomes progressively, you see heightened levels of ACTH in the blood because it's not being cleared away, and that feedback loop is broken. And then the stage 4, the clinical Addison's disease, is actually when you have basically no cortisol in the blood and the ACTH levels are very, very high. And this is basically considered adrenocortical failure. And the way that you actually can diagnose this is you can actually artificially stimulate the adrenal glands with ACTH. So you do the ACTH test and you measure the output cortisol level. So you're basically testing this feedback loop. And this level of response, the adrenocortical failure, is considered the clinical stage of Addison's disease. All right, and to talk about the system description for natural cortisol production, we can model this as a second order system. This is primarily, so this X1 is basically modeling the cortisol concentration within the adrenal gland, and X2 is basically the value that we care about, which is the cortisol concentration in the bloodstream. There are two rates that are very important. So you have theta 1, which is basically the infusion rate of how fast the adrenal gland is released into the bloodstream. And then you have a clearance rate, which is then how fast the cortisol is cleared from the bloodstream. And what we're basically saying within this system, that in natural cortisol production, this system is very healthy. However, in Addison's disease, this adrenal gland system is no longer responsive to the ACTH stimulus, and therefore theta 1 we can consider essentially zero. All right, and now in terms of treating Addison's disease patients and replacing the cortisol levels when the HPA axis is no longer able to naturally create cortisol. Typically, this is replaced with hydrocortisone, which is basically, you can think of it as a synthetic cortisol. It has a high affinity binding to the glucocorticoid receptors, and it's also very flexible in the way you can dose it, so it's very useful. So the typical scheme is oral dosing, so a pill, which is 2 to 3 to 4 times a day, to mimic the circadian rhythm at a very simple level. Another way is topical, which is basically like a lotion applied on the skin. And more flexibly, that's very interesting, is external pump infusion. So you can inject hydrocortisone subcutaneously. And this is very beneficial from a control perspective. One thing to mention that's very important is kind of the dosing limit and the dosing range throughout the day. This is very important to maximize patient quality of life. So the typical daily dose is 15 to 25 milligrams. And if we're under this, then we often will run into the typical Addison disease patient syndromes. So fatigue, weakness, impaired stress tolerance, and then in a severe case, if there's a stressful event, we can actually have an adrenal crisis, which is significantly life-threatening. If we're over replacing, because this is a steroid, oftentimes this has a high association with osteoporosis, losing bone mineral density, and also hypertension. And because this is also a synthetic cortisol, what we'll have is we'll run into Cushingoid syndromes, which is basically too much cortisol in the blood for an extended period of time. There's one event or one study that showed that chronically overdosing using a subcutaneous pump can actually gave one patient refractory hypokalemia. So this is a very important kind of dosing bounds within our system that we want to stay within the typical daily dose for a chronic period of time. Now, the dosing strategy and the choice of how you're delivering hydrocortisone is a very important selection that governs how much and when and how much temporal resolution you have in terms of delivering hydrocortisone to the patient. So the standard or traditional approach has been oral tablets, which is, let's say, a fixed schedule of 2 to 4 tablets a day. And one aspect of this is that this is then ingested, it's metabolized through the liver, and then released into the bloodstream. So there is a significant delay from basically when you take the hydrocortisone tablet and then when you actually see the hydrocortisone or cortisol level within the bloodstream. Another significant problem with this is because the natural circadian system that creates cortisol, you need this production of cortisol while you're sleeping. You can't take an oral pill while you're sleeping, so this is another limitation that kind of limits the amount that we can approximate to the healthy circadian profile. So this is an example of what this may look like, where you're taking 2 tablets a day, where you have these basically cortisol deficient areas that are very important, and during these periods of the day, this is significantly risky for the patient, and also reduces their levels of energy and health throughout that period. So this is not optimal from a control perspective. Now, a more interesting approach is using continuous subcutaneous infusion, which is basically a pump. And this has actually been shown we can use similar pumps that already exist on the market. For example, the Medtronic glucose pumps. And from a control perspective, this is a lot more interesting because we can program and in any period of time the delivery rate of hydrocortisone. So there's much simpler also absorption. So subcutaneously, we're bypassing the liver, and it has much simpler kinetics and much more programmable. So essentially, we can do real-time control. So this is very interesting from a control perspective to develop an optimal system. Okay, with that said, the goal of this work was to develop optimal closed-loop control of cortisol in Addison patients using the continuous subcutaneous hydrocortisone infusion. So we wanted to within the constraints of hydrocortisone to maintain the daily dose within the healthy therapeutic range and also minimize the patient deviation of the actual cortisol reference or the circadian rhythm compared to the healthy reference cortisol profile. The first step was to develop a model for how hydrocortisone is delivered to the bloodstream using the pump instead of the HPA axis. So this is a model of the natural cortisol production, where you have the adrenal gland in the bloodstream, and instead, when you're replacing the system, because this is no longer functional, you have a CSHI pump, which is delivering hydrocortisone to subcutaneous tissue, and then this is absorbed by a factor of K or by a rate of Ka into the bloodstream, and then cleared by the same rate of K, which is essentially the same as theta 2. The difference between the K absorption term and theta 1 is that theta 1 is meaning the absorption rate from the adrenal gland into the bloodstream, and what this is saying is basically the absorption rate of hydrocortisone concentration into the bloodstream. So we do have a similar second order model, but it is slightly different in terms of what the X1 term means. So Ka is the subcutaneous absorption rate. K is very similar to theta 2 in the plasma clearance rate. U of T now becomes, instead from a pulsatile ACTH input, it's now a pump delivery rate in terms of micrograms per minute. We have this H term, which is basically a factor conversion that relates everything from X1 to X2 to be in terms of concentrations. So hydrocortisone concentration and cortisol concentration. And X1 tilde is basically that normalized concentration value, so that within the subcutaneous tissue. And then X2 is the value that we care about, which is the same thing as in the endogenous cortisol production, which is blood cortisol concentration in micrograms per deciliter. With that said, what we have is 34 healthy patients that we use as a reference that we want our patients to follow. So the healthy data set, this is basically a 24-hour sample of cortisol profiles throughout the day with a 10-minute sampling period, and we use these as the target for the patients to follow. Our patient data comes from a separate study of 4 patients using fixed rate continuous subcutaneous hydrocortisone infusion, and that basically a rate scheduled fixed rate pump dosing throughout the day. So they also come with the body surface area, the fixed scheduled TSHI dose, and then the patient cortisol levels. And what we use that model that we'd previously developed to then estimate their absorption and clearance rates, and then we have a full characterization of 4 patients with Addison's disease. They are all clinically confirmed to have Addison's disease, and this was basically studying the previous study was looking at basically how fixed rate dosing can restore the circadian rhythm, and optimal control that's personalized to their specific parameters is going to do a much better job and also remain within the dosing constraints of the of hydrocortisone. Now, with the model structure fixed, the patient-specific parameters, K absorption and K clearance, are estimated by fitting the 2-compartment model to each patient's observed dose response rate. Basically the fitting procedure is a constrained nonlinear least squares problem, and given the patient's known pump infusion schedule and their measured cortisol samples, we find the values of Ka and K that minimize the sum of squared residuals between the simulated plasma output and the observed measurement. So this is basically on the left here, we have the fixed dose. We have the propagation of hydrocortisone through the first compartment, which is the subcutaneous tissue, and then into the plasma cortisol. So now we have the absorption and clearance rates for all 4 of our patients with reasonable R-squared values. Okay, now that we have the parameters estimated, we then develop the full state space planned for each patient. So we have the system matrices A, B, and C. C is 0 and 1 because we only measure the blood cortisol concentration. H is our normalization factor that we apply directly to the input so that everything beyond that is measured in a concentration. And because negative, we have the eigenvalues of negative Ka and negative K. This is a fully stable system. And what this looks like from an open loop perspective is all of these eventually decay to zero, with decay constants from 135 to 260 minutes. Um, so this is basically what the patients would look like without any treatment, and if they were to start at an initial cortisol level, within a day, within half a day, they would actually have zero cortisol within their system. And this is basically something we want to resolve, where we want to restore this into a circadian rhythm. So then we develop a controller and an estimator to control this. So to augment this further with our plant and to simulate also the measurement of blood cortisol and the noise associated with both the plant and also the um, measurement, we augment the system with both process noise and sensor noise. And then we develop a Kalman filter as our estimator to estimate the X2 value. So we use a continuous time Kalman filter as our estimator and augmenting this process noise and sensor noise with Gaussian noise. Okay, now for the controller, we formulate the LQR problem where the cost function J integrates two terms over time, which is the state penalty weighted by Q LQR, and then also the control effort penalty weighted by R LQR. So we chose QLQR to be C transpose C, which penalizes X2 only, which is blood concentration. And we know that's correct because what matters clinically is blood cortisol and not the unobservable subcutaneous tissue concentration. RLQR is a scalar control penalty that we optimize for, and this becomes approximately 150 to 300 for each of our patients, and that was shown to show closed loop poles that are stable across all of our patients. So then we solve the algebraic Riccati equation, which yields the optimal feedback gain for K LQR, and that pure state feedback basically regulates to zero. So it doesn't track any referencing. So we need to add also a feed forward channel, which is N. And this is a scalar feed forward gain that's derived from the DC gain of the closed loop system, which uses the final value theorem. And then what we have is the actual total control law, UT, is NRT minus KLQR, which is we have both the state feedback gain and also feed forward. Now, to make our control law physically realistic, we need to add a few saturation terms to the maximum and minimum bounds of what our system can actually deliver in terms of U, or our dose, or our hydrocortisone dose. So obviously we can't pump a negative amount of hydrocortisone into the subcutaneous tissue, so we need to have a maximum or a minimum bound of 0, and we also set from a reasonable level so that we don't have an extremely high rate at some point to be 2 milligrams per minute. This is like a typical maximum rate for CSHI pumps in a standard mode. All right, now putting all this together, we have our closed loop architecture here. We have the reference circadian profile RFT, which is the profile of our healthy patients. This feeds into the feed forward gain N and then the observer. The pump command U of T is then saturated before it reaches the patient. And then the patient plasma cortisol Y of T is measured and fed back into the Kalman filter, which reconstructs both states. And then the feedback gain K LQR then closes the loop. And then in practice, commissioning this controller for a new patient, this will require 4 phases. First, of course, we need to measure their BSA and run the fixed rate CSHI sampling their profile. So basically do the estimation loop that we're talking about. We solve the constrained nonlinear least squares to estimate the absorption and clearance rates, and then assemble our ABC parameters for the state space model of the patient. We then solve the LQR and Riccati equations to find our KLQR, L, N, and M matrices, and then do the saturation with either this maximum rate or something else with the saturated U of T dosing law. All right, now this is an example of the multi-day reference tracking that we had done for each patient for each healthy reference profile. And what this is showing is we have the blue line, which is the Kalman filter estimate following the Y of T, which is our measured value. And then this purple U of T is the dose throughout the day. And then the green is, of course, the reference that we're trying to follow. And basically what we had done, we observe the plant response across 3 circadian days and integrate the dose throughout the day to see what their actual hydrocortisone dose was per day. So the reference tracking was measured with NRMSE, and we then measure also the dosing strategy or the dosing amount throughout the day to evaluate the performance and dosing required to bring this patient to follow the reference profile. Now, this is probably the most important result in terms of directly comparing our work versus these same patients on the fixed rate CSHI pump from the previous work. This showed that we were able to actually reduce the total hydrocortisone dose for each of these patients between 6 and 29% for each of these patients. And especially 5 and 6, which had uh, much faster absorption rates, they were able to reduce it much more significantly. But this is an important result in terms of how we were able, basically saying that we were more accurately able to restore the circadian rhythm while also reducing the hydrocortisone dose within the healthy range. So this is very important. So the same patients previously, they had, for example, patient 1 had 19.4 milligrams per day, and then we were able to reduce this from 18.2 on as a mean. For patient 6, this was from the original dose that they had was 23.7, and we were able to reduce this to 15.55. So that's a significant result in terms of dosing reduction that is very important for example, reducing osteoporosis or hyperfractorykalemia. And this is very, very valuable in terms of also doing the reduction while also restoring circadian rhythm. Okay, and in terms of limitations of this model, we do have a number of important things to mention here, which we can probably group in terms of how we model, in terms of how we scope our work, and then in terms of how we identify patients. So one thing in terms of modeling is we made the assumption that the adrenal gland in our system is essentially non-functional, or there's negligible or zero cortisol. And what this means is we're restricting our model to clinically diagnosed Addison's disease patients. And what that means is we couldn't apply this necessarily to earlier stage patients who, for example, would have stage 2, stage 3 Addison's disease progression. They still have some residual cortisol within their X2, and maybe their adrenal gland is functioning somewhat, not to the extent that it's a natural or healthy adrenal or HPA axis system. But it is able to operate effectively in releasing some residual cortisol. And one way to model this, we can add a baseline term that models that residual cortisol that exists. This is done in previous models that might make this a third order system and complexify how we model things. But this would be one way to alleviate the kind of restraint on only working or only modeling clinically staged Addison's disease. And then in terms of the scope, one thing that we did in terms of our modeling or simulation was we only studied the chronic circadian tracking. So there are two things to mention here. One is that previous work does show that the absorption and clearance rates do change over time, and this is something that would need to be tracked and maybe continuously updated and personalized to each patient. So that's very important to mention that we made the assumption that all our patient parameters are essentially static. So if we were to model this for the period of, let's say, a week to a month to a year, our simulation results would be steady, but in terms of physiologically realizing this onto an actual patient, we can't necessarily make the assumption that those rates are going to always be the same. So this would either need to be re-estimated over a period of time or modeled in a different way. And in terms of the scenario that we measured, of course, our goal was to restore to a healthy circadian reference. But another important aspect of this that our controller would need to be able to deliver is up to 3 times more cortisol in a high stress scenario. And that's very important it's because it's very life-threatening to have the adrenal crisis. So being able to model the acute stress response is also very important. And then some things about the identification where our patients were only female. And for 2 of them, we actually had to do a salivary to serum conversion, which did introduce a significant amount of noise into the initial blood cortisol concentration that we use to estimate their patient parameters. And for that reason, we would say that 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 estimation would be not preferred compared to, for example, having directly the cortisol blood cortisol concentration levels that we can use directly. So in that way, what we would say is to prescribe this to a new patient, we would say absolutely the blood cortisol would be what is preferred to be measured to do the estimation step to estimate parameters. All right, and to summarize, basically we were able to design an optimal closed loop control with the continuous subcutaneous hydrocortisone pump that does demonstrate that we can restore the chronic circadian rhythm and ensure the safe dosing for all four characteristic Addison patients. All of them were able to track within that 15 to 25 therapeutic window for hydrocortisone, and with a reasonable amount of tracking error compared to the reference profile. They did also show, compared to fixed rate dosing, that we're able to have a very safe reduction of hydrocortisone compared to the original study. And as I mentioned, the future work would involve, for example, the acute stress or crisis response modeling, the realization of the high frequency plasma cortisol sensing. This is also very important. Basically, the assumption that we can continuously measure blood cortisol is very important to actually feasibly realizing this as a real system. And then residual cortisol to extend this to early stage patients. And thank you.